everybody. Welcome to Liverpool John Moores University and to what I believe is the fourth Professorial lecture of the year for the School of Sport and Exercise Sciences. It's not the faculty Christmas party, so if you wanted to go to that, you're in the wrong place. But also, it's a nice way to finish the year with Jatin's Professorial receipt. So it's my pleasure as the Director of the School to introduce Jatin to you this evening. So Jatin is described as a pioneer of proteomic investigation, which is a relatively young discipline with the first studies of heart and skeletal muscle proteome emerging in the late 1990s. Jatin published his first work in this area in 2007. Jatin began his life at LJMU as a PhD student in November 2000, but more in the area of molecular physiology. He was then funded by the British Heart Foundation and then undertook a postdoctoral position under the guidance of Professor Dave Goldsmith, who is here tonight. So welcome to you, Dave, and also some of the colleagues. He was awarded the British Heart Foundation Junior Fellowship in 2004 and was appointed as Senior Lecturer in the School in 2006 and progressed to Leader in 2010. Now, before all this, you may not know this, but Jatin was trained as a mechanical engineer. So he is actually an engineering industry trained and qualified time-served toolmaker. So unfortunately, this skill set has not allowed him to repair the kit and equipment in the lab that he uses. So I have a suspicion that this evening may be some subtle hints, or maybe some less subtle hints, as to how much money it's going to cost us to continue the function of that lab. Jatin was a strong contributor to the REE 2008 and also the REF 24 submission, and his work in developing muscle physiology in the proteomics lab, the only facility in the UK and one of the few in the world. This positions Jatin and ourselves as a world leader in the application of proteomic techniques in exercise physiology. With over 60 peer-reviewed publications, Jatin has published more articles in this field than any other single laboratory. His current H index is 23, and he has over 1,400 citations of this work. In addition, he's also generated over £1 million worth of income in research grants, and he has 8 PhD completions with another 2 in the pipeline. He is undoubtedly a world leader and possesses a clear vision for the future of proteomic investigation within the school. Jatin is a well-established and well-respected member of staff and a genuinely nice guy. I had something in there about the comfiness and the coziness of the office, but go into that one. But he's got extremely high standards across both his teaching and his research. He's also the program leader for our Masters in Exercise Physiology, and he's demonstrated the ability to develop innovative research-informed techniques and develop the program and stimulate to include a stimulating and exciting environment for these students. So this juncture is one of the things where you try to identify, try and get a little bit of information about Jatin from some of his colleagues, and then sort of embarrass him in a particular way. But there was nothing really out there for Jatin, but he is just a genuinely nice guy. But I have managed to get an extract from one of his students. It's nothing like that, I'm afraid. It's just really nice. So. I'm extremely lucky to have Jatin as my Director of Studies. He's always offered patient guidance, encouragement and first-class advice throughout my time as a student. Jatin is a genuinely inspiring academic, he's a true pioneer in this field. I've never met someone as knowledgeable or committed or who holds genuine love for their work as Jatin does. He remains my best role model for a scientist, mentor and teacher, and is the reason why I decided to pursue a career in research. His enthusiasm and love for his work is contagious. His unrelenting support, often doing above and beyond, is, in my opinion, unparalleled. Jatin continually works hard to firefight the concerns and anxieties of his students in an increasingly complex subject, which has helped to instill great confidence in both myself and my work. This tireless attitude and endearing generosity distinguishes Jatin as one of the best, and I thank him for the job he continues to do. So I received that, I thought that's my job done. A fantastic testimonial for Jatin and his work and his support for the students. So without further ado, ladies and gentlemen, distinguished guests, hopefully with a low-cost presentation, Professor Jatin Burniston.
Thank you very much, Dave. I'm not sure I can top my introduction, that's the only problem. But I'll try. And so, thank you for the introduction, and I'd also like to thank so many people for turning up today as well. Obviously, it's a busy time of year, so probably in hindsight, the week before Christmas isn't the best time to try and schedule one of these lectures. But hopefully, in the spirit of Christmas lectures, I can give you something that's educational and a bit of fun as well. Or at least that's what's planned. So, to begin with, I'd like to just say the title, what I was trying to get there is this question, and this is what I spend most of my time thinking about, this question of how does muscle adapt to exercise. So tonight I'm going to try and convey some of my research story. But before I do that, I feel kind of duty bound to try and explain how it is I got here. Because like Dave mentioned, I didn't take a normal path into academia. And in fact, in writing this talk, I looked through my past paperwork and I found my high school record or the results. And during high school, academic path clearly wasn't set out for me. In fact, I managed to leave high school with only one GCSE, and that was a grade C in modular science, so I'm not sure how that affects my post here as a professor. So really it raises the question, how do you get from grade C modular science up to professor in science? And of course the help is, the answer is with the help of a lot of important people, and it's those people that I'd like to try and thank first of all in my talk. When I was preparing this talk, I sort of realised that my research question, the key components of it, can be traced back to different parts of or different times in my past, and that's what I'm trying to show here. And as we've already established, I didn't pay much attention in school, and here's a picture of me from school days, so you can see what they were dealing with. But I have always been interested in this question of how, and I attribute that to my parents. So I grew up on a farm in Yorkshire, and this is my mum and dad up on the farm, and they're looking very happy there. And it's probably this picture was taken before I became a teenager. But my parents did a very great job in instilling this question of how, or this desire for knowledge. And I'd like to thank my mum first of all, because my mum's not a professor, but I think in many ways she should be, because she spent a lot of her life studying and taking courses, but even in between that, through our childhood, we did things like experiments with everyday objects, and I can remember a time before cooking the turkey for Christmas, we had to do a dissection on it, things like that. So there was always this sort of educational environment, and I'd like to thank my dad as well. Here's a picture of me driving a tractor. You can just about see me and my dad driving a combine harvester. And when you grow up on a farm, you get to do cool stuff like this. But on the farm, there's also lots of things that need fixing. And it seemed to me growing up that my dad could fix just about anything. And I spent a great deal of time watching him and helping him. Well, I thought I was helping him. And, fix everything from gates and fence posts to washing machines, tractors, combine harvesters. So I had this always had an interest in the how. And at that stage, the thing I was most interested in learning how it worked was motorbikes. And so as soon as I finished school, I moved across to South Manchester and I started a motorcycle mechanics course at Stockport College. And then later on I worked as a motorcycle mechanic and I joined a bike club. And here's a picture of us going back in those days, and hopefully you can pick me out. I'm towards the left hand side there. And next to me, I forgot to do the lights, so okay, maybe that's as good as the lights get. So next to me is my best mate Brian, who's I'm very pleased to see is here with me today, and well, Brian's helped us right throughout our lives, but in particular, he was a strong role model. No, we're not going to get very far tonight. He was a great role model, and he did a great job of keeping me at least moderately under control. That's what I want to say. So I spent time learning how to fix bikes, and but then my interest changed from fixing them to wanting to know how to make them. And next I trained as a tool maker. And oh sorry, see, it's not going to work tonight, is it? I was going to say, because I often get sense when I tell people nowadays that I was a biker, they immediately think of the TV series Sons of Anarchy. And sometimes I can see in their eye, they're thinking, how many people has this guy killed? So here's a picture of me in the middle of an intense gun battle, just so you can get the correct picture. So I'm still into my bikes today. Here's my transport to work, and here's a recent project I've worked on. But as I was about to say, I was now moving into the idea of being able to make bikes, and so I trained as a precision engineer or a tool maker. And in case you don't know what tool maker does, they use machines like lathes and milling machines to fashion metal. And I specialised in an area called plastic injection mould tools. So this isn't one that I built, it's just a picture I pinched off the internet. But it gives you an idea of what an injection mould tool looks like. It's basically a really fancy jelly mould that plastic is injected into, and they're used to make lots of everyday objects. So that's not mine, but this is a picture of something. It's a handheld little pick that you use for cleaning your golf clubs, which doesn't seem much, but I'm really proud of this because this is the first thing that I made the tool for all by myself. So I was very pleased to get to that standard where I could create the whole product. Now, what happened then was something quite bold and probably looks very stupid at the time. So I spent probably 5 or 6 years training to be a tool maker, got to being time served and officially qualified, and then I found that actually I didn't really like the day-to-day business of tool making, and so I quit what was a perfectly good, highly skilled job that I'd spent years training for. I didn't really even have anything else to do. What I did have though was a new sort of interest in Thai boxing or Muay Thai, and this is being a few clips of me from years ago doing Thai boxing, in case you don't know what it looks like. I should say it looks much more elegant when the Thais do it rather than when I try and do it. So that was my new sort of interest, and probably what not probably is what got me into the area of sports. And I have to thank Master Sken for this. I was quite lucky that Stockport just happened to be kind of the centre of Muay Thai in the UK, and I trained with Master Sken, who was the original Thai master who brought Thai boxing over to the UK in the 1970s. And as I say, he's an original Thai master, so working with him, I spent a lot of time with him and became his lead instructor of the headquarters. And he was, again, a very strong and positive influence, teaching me about discipline, humility and grace. So that was a very inspirational time. I suppose quite naturally, I started Thai boxing. Immediately I wanted to know how does exercise work, how can you train better, improve performance, etc. And so I went back to college and enrolled on a BTEC in sports science. Well, actually, sorry, I should say I tried to enroll in a BTEC in sports science, but they wouldn't let me because I didn't have any GCSEs. So after a bit of negotiation, they took my engineering background as evidence that I could do maths, but I still had to do an English GCSE at the same time as doing my BTEC studies. So I spent my days doing sports science in the daytime, Muay Thai any time that I could, and I also worked in Manchester City Centre as a doorman, at weekends, to get some money in. And to begin with, I was just doing sports science, as I say, to learn how to improve performance, etc. But then something very important happened, and my girlfriend and now wife became pregnant, and we had our first child. And that was a really sort of important, pivotal moment in my life. It brought a change in perspective in me. And anybody who knows about changing behaviour, if you change someone's perspective, then it can have very profound effects. And that's what it did. It gave me a new drive. I'm not sure how much I noticed it at the time. But it drove me forward, it drove me to want to develop a career and basically stop messing around. So up until then, university had never popped into my head. I don't even think I knew a university existed, but then all of a sudden it seemed possible. So I filled in the UCAS form, etc., and I went to the University of Portsmouth. And it didn't, I can't remember the process exactly, but it didn't seem to worry us at all. That Portsmouth was 250 miles away from our friends and family in Yorkshire, Manchester and Anglesey. But, you know, we moved down there and I studied, and it was certainly a very tough time, but one that I look back on with very fond memories. Again, I studied in the daytime. I started a Thai boxing club there and taught in the evenings to raise some money. And at this stage, it probably sounds like I'm some sort of dynamic hero. But there's actually an unsung hero here, and that's my wife, Sarah. Because during our time in Portsmouth, Sarah had our second child, and still found time to work as well as all of our. I'm sure I will get better when I get into the normal science bit. I'll be better. So, and you know, I don't know how we fitted it into the 3 years, but she managed to work and support our family. And just to give you a glimpse of some of the things or one of the things that I put my wife through, this is, see if I can see her crying now. This is a picture of us after my graduation ceremony. And anybody who sat through a graduation ceremony will know they're not great entertainment for toddlers. And you can look at the expression on my son's face, and that's not a face that says social etiquette. And you shouldn't be, you know, deceived by my daughter either. She can just as much as a handful. But nonetheless, my wife managed to get these two through the ceremony without the building having to be evacuated. So it was great. And the other thing that happened while I was down in Portsmouth was that I learned about muscle physiology, as many sports science students do, and I learned how muscle is a very structured tissue made up of bundles of myofibers, and each of these long myofibers is made up of a series of what's called sarcomeres. And if you want to get an idea of what a sarcomere or how it works, then you can put your fingers together like this and move them in and out, and the shortening of those sarcomeres is how muscle contracts. Which seems simple enough, but it was quite a profound thing to me. And I can still remember being in a second year lecture by a lady called Christine Body, who actually worked in Liverpool as a technician for RHD Edwards, who's a very famous muscle physiologist. And she showed a little PowerPoint cartoon, a bit like this one, where she shows the two major muscle proteins in muscle, myosin and actin, working together to shorten, and this is what produces the force and the shortening of muscle that's the basis of all human movement. And it was very simple. It was much more crude than this brilliant animation here. But I was hooked from that point onwards. I was hooked, and I think it's because it was the kind of the interaction between the past in mechanical engineering and the new love for physiology. So I read as much as I could about muscle physiology. And when you read about muscle, then one of the names that pops up all the time is Goldsmith. And so I was absolutely delighted that when I finished my degree, there was an advert for a PhD with Dave Goldsmith at Liverpool John Lawrence University. And so I went up, and I remember interviewing, and Brian took me to the interview, and I got a really good grilling. I still remember that interview very fondly now, not so fondly back then. But I got the post, and during my time with Dave, we investigated the effects of a drug called Burniston, and we were trying to find a dose of this drug that could be used to promote muscle growth without causing any muscle cell death. And to do that, we used microscopy, and we looked for muscle cell death in the heart and skeletal muscle of rats that had been given different doses of Burniston. The top panel is what a normal heart should look like. The bottom panel is a skeletal muscle, a leg muscle of a normal animal, stained blue so you can see the fibres, and then these images show muscle cell death, stained brown. And I'm very happy to say that our work, we did a series of studies, and our work contributed towards the safe use of clenbuterol in some forms of cardiac surgery. So it was very pleasing to be able to, just from a short PhD study, feel like I've made a contribution to a wider body of work. And I've got to say that during my time studying with Dave, I was under absolutely no doubt that I was receiving the top class research supervision and academic mentorship. Well, probably what I realise is now, what I didn't realise at the time is all the things that Dave was teaching me then that I would need later. And I think that's just absolutely amazing. And I've just, I'm lost for words to know how to express how grateful I am today. All I can say is that, that's what's inspiring me to be a good supervisor, and hopefully I want to be as good a supervisor as Dave is. I'm not the first professor of Dave's student. I think I'm the sixth, is that correct? So Dave has supervised and created 6 professors that have then gone on, and think of how many people he's influenced. So thank you very much, Dave. One of the last things Dave gave me was this thing called proteomics, because without him I think I would definitely miss the emergence of this new research field. And proteomics is studying proteins using omic techniques, and that essentially means techniques that have been made possible from the sequencing of the human genome. And as for the reason why I'm using or interested in proteomics, then I'd ask you this question, and that is, what is it do you think it's made of? Now, I don't know about you, but I was always told that little boys are made of slugs and snails and crocodile tails. Little girls are made of sugar and spice and all things nice. But now that I've graduated from modular science up to professor, I can tell you that's actually not true. We are in fact made of these, mostly made of these 4 elements anyhow, and these elements are arranged in different ways to make different molecules. You're not leaving already. And the most common of these is water, which is hydrogen and 2 oxygens. So about 2/3 of the body is water, and then the other third is solid matter, and the most common component of that solid matter is muscle. Oh, sorry, it's protein. Forgetting the wrong subject. And we've already seen 2 very important proteins in muscle, actin and myosin, but just that sarcomere structure actually has at least 50 other proteins in it, and if we extend our gaze out to the whole cell, then it takes several thousand proteins in order for a cell to work. And it's these proteins that I'm interested in measuring. Now, proteomics and the development of post-genomic techniques gives us a new way of looking at research as well. So previously we would have used targeted techniques, such as again this microscope image, where the fibres have been stained different colours of grey or different shades of grey, depending on whether they're type 1, 2A or 2B. And these different types have different functional characteristics. So a traditional approach to a research question about muscle would involve you thinking about a question, generating a hypothesis, and then using a targeted technique. So you might think or hypothesize that an athlete's muscle would have more 2A fibres than a sedentary person's, and that's because 2A fibres are more powerful. Then you'd recruit some participants, and then you would measure the amount of this particular protein in each muscle. And you very likely find that indeed, yes, the active people have more of the 2A fibres. And that's all well and good when you're dealing with well-known and very important proteins like myosin that have a really obvious effect on muscle function. But as I said, there's thousands of other proteins that are also required for muscle function, and it becomes much more difficult to come up with sensible hypotheses. And that's where the proteomics or discovery science techniques can be used. And so we start with a much broader question of, or broader statement, such as we know a population of athletes can run faster than untrained people. So there must be something different about the muscle between athletes and untrained people. And based on that basic premise, we take muscle samples, we analyse hundreds or thousands of proteins, and then we plot the data on a graph like this. And when we do this sort of work, we find that a lot of the proteins are the same in either the sedentary people or the athlete's muscle, and they're plotted in the middle. But then there are some proteins that are much more abundant, so they're more important in the sedentary state, and there are some proteins that are more important in the athletic state or well-trained state. And we can look into those groups of proteins and find networks in how they interact together. And very often we see that some of those proteins are well known, so some of them might be myosin, for example, and then other ones are hardly known at all, so we know very little about these proteins, and they become the target for the next hypothesis-led research. So this is a very new way of doing science, but it's proving to be very powerful, and it's one of the reasons why I love the subject area, because I feel that it's allowing the muscle to tell you what's important, whereas often I feel that the targeted research, the scientist is putting in their opinion of what they think is important, and history tells us that we're not always right. So that's the kind of the idea of the experiment design. The main technique that's used, the reason why we can do this, is mass spectrometry. And I just very quickly want to show you the workings of a mass spectrometer. Don't get too worried. It's just a simple overview. So essentially a mass spectrometer has a source where we put the sample in, and then something to measure mass, in this case a time of flight analyzer, and it works by first of all firing a laser to get our sample into the gas phase, and then they're fired through the analyzer and they hit the detector. And the speed they travel through there is relative to their mass. So what we end up with at the bottom is a spectrum of masses. And here's some real data in case you're interested. And this spectrum of masses is actually specific to that protein. In fact, we nicknamed this technique peptide mass fingerprinting. So from this we're able to identify proteins, and we don't need to take a targeted approach. We don't need to know what the protein is before we start the experiment. We can also measure the abundance, so the amount of each protein, by measuring the height of the peaks. And last of all, we can get very detailed chemical information. By zooming in, we can see that each peak is actually made of a pattern of smaller peaks. And if you remember, I said we're all made of these four elements. If you zoom into any of those elements, then each of these has a nucleus with protons and neutrons surrounded by electrons, etc. Take carbon as an example, then most of the carbon in the world is carbon-12 because it's got 6 neutrons, 6 protons in its nucleus. But we also know that there's some carbon in the world, about 1%, that is heavy, so it's carbon-13 because it's got an extra neutron. And what this spectra here is showing you is that the protein contains some of the carbon-12, some of the carbon-13. So the mass spectrometer can identify the protein, measure its abundance, and give us very detailed chemical information. And we can use this particular chemical information in a new technique now, because it's not just carbon that has heavy isotopes. There are other things like hydrogen as well, and there's a thing called heavy water, which we can have people drink while they're undertaking a study. And when they do that, every new protein that's made has some of the heavy label added to it. It changes the shape of that peak pattern, and we can use that change in shape to measure the amount of new protein that's being made. Okay, so that's probably enough chemistry and mass spectrometry, I think, for a Friday evening. So next bit. Could be the next Transformers film, I guess. Mass spec versus microscope. It is, in fact, a comparison I'd like to draw, because I've shown you some microscope images, and people have been trying to magnify things for as long as we can remember. But really the first acknowledged scientific work in using the microscope was Robert Pogue in the 1600s, so more than 300 years ago. And he used a simple microscope to look at things like this flea and also man-made objects. Over the past 300 years, the microscope has obviously developed greatly, and we're now at a stage where we can take full colour images of single cells. So it's a very important technique in research and teaching, and I would say that every university in the world has rooms full of microscopes that are used for research and teaching. Mass spectrometry is a much newer technique, so the first protein mass spectrometry was performed in 1987, so 30 years ago, and since then the field has developed, and these are publications that have used proteomics either in muscle or in exercise. So as Dave said, the first one was just at the end of the 1990s in muscle proteomics. I found out about proteomics probably around 2002 or 3 when Dave mentioned it to me. And then I trained in the proteomics lab at Professor at the University of Liverpool. And around that time as well, I was really very fortunate to receive a lot of support from Tim Cable at the school and the university in the widest to be able to establish my own proteomics laboratory. And it's just a fantastic gift to have that much support for something that was so new and a new idea, and it's really allowed me to develop a research career driven around this question. So I published my first work in exercise and muscle proteomics in 2008, and it was the first of its kind. And since then, as Dave says, it's made me sound a lot greater than I think I am. But I've kept on publishing, and the field is developing, and I think it's set to accelerate now, because in the last couple of years, some of the most famous exercise labs in the world have started to take and use proteomics. So I think one day, first of all, one day the things that we're doing now will be looked back upon as the drawing of the flea from the 1600s. And the other thing is, I genuinely think that one day every university will have rooms full of mass spectrometers that are used for teaching and research. So to finish with that, well, not quite finished, but for the next part, I'd like to show you and demonstrate to you our most recent work combining mass spectrometry and heavy water labeling. I've already said that we can detect differences between perhaps an untrained population and a trained population, but in fact what's more interesting is to say, well, what's changing if you take some people that are untrained, sedentary living, and then train them and try and change their muscle into something more like an athlete. And that's important because we know that that's associated with a lot of health benefits, and indeed the health side of this is most of what's driving my research questions nowadays. First of all, of course, you need to get somebody to do the exercise, but then what I'm interested in is how do we change from one muscle, from the orange muscle, through to the blue muscle. And so to do that, we've got a practical demonstration. Because it is a Christmas lecture, and as great as Dave says I am, I'm not sure I'll ever get invited to the Royal Society to give the BBC Christmas lecture. So I thought I'd make my own. Thank you very much, Gemma. So we couldn't get Lego bricks that match the perfect colour, but what we have got here are two different colours, and these represent the different. Sorry, I should say, I've just jumped up, I didn't even find it. This is my daughter, Kira, and you see she's grown up a bit. And this is my son, Leon. You see, he's going up a bit too. So these two colours represent either our untrained muscle, and we're trying to make it into a trained muscle. But first of all, can you two swap round actually? Because when I pictured it in my head, it was the other way around. I must say, we've tried to rehearse this, but we haven't really had time. So the first thing I want to say is that all the proteins, you've snipped them all already. in the cell, how do we change? Well, the thing that enables a muscle or any cell to change is a process called turnover. So here, my son now is going to be synthesis, so he's going to be making new protein. Each one of these represents some protein. It's quite a good model because proteins are made of building blocks, amino acids that is. And my daughter's going to be breakdown. So if breakdown could begin, so breakdown's working all the time, and synthesis is working all the time. I realised today I was going to have to get on there. So we have this process called turnover, and it's basically recycling. And that's working all the time in our cells for all of our proteins. We have the proteins being made and broken down all the time. And this is an important process because it keeps the quality of our muscle high, so if it's not working, then it can lead to disease. But it's also what enables muscle to adapt. So now, as the muscle protein is being turned over, if I take the job of being gene expression and start to say that actually what I want is a trained muscle, so I can start giving synthesis some trained muscle to work with, and it can start making this muscle for me. So now slowly we end up with a process where not only we've got turnover of the protein pool, but also we've got new protein coming in, which is associated with good exercise performance and good health benefits. And we can carry on like this. Synthesis is cheating. And we can carry on like this. And in this role, I'm being gene expression, I'm giving the instructions. But the problem is, very often the instructions, so what the body wants, what it thinks it wants, it doesn't actually get. And that's often because sometimes synthesis ignores gene instructions. So I might be here trying to get him to make with the yellow one, but synthesis might just be ignoring me. And in fact I realise this is probably quite true because my son mostly ignores me. Or even if synthesis does listen to me, then we could have a scenario where degradation or breakdown decides to be selective. And therefore, no matter what synthesis is doing, the breakdown is selective, so it's cancelling out everything that synthesis is trying to do. And this is a particularly difficult question to try and get information on, because we can't really see what breakdown is doing. And that's because everything that breakdown does goes in the bin, and we can't analyse it. Okay? So that's the process of turnover and how we might be trying to change muscle during exercise training, or indeed any other stimulus. The next thing I'd just like to try and demonstrate is a change in size, because the other thing that might happen is with resistance exercise, for example, as your muscle gets bigger. So one of the things that happens might be if synthesis works faster. I should have brought some chocolate biscuits, that would have made it work faster. Then you can appreciate if synthesis speeds up and breakdown stays the same, we're going to end up with more bricks on the table, aren't we? So the muscle is going to get bigger. But you can also have muscle growth from the process of synthesis staying mostly the same, but breakdown decides to knock off, okay, or slows right down and can't be bothered breaking down the protein. And in fact, so you can have these two different sides to changes in muscle mass, and really, so in fact, it's a case of both of these working, so it's a relative change in these two things. Well, let's say they're working away and we can give them some more bricks to work with as well. So we can have all sorts of, so we can have lots of different proteins. So it comes in, the question comes, how do we measure what's going on? And one of the ways we can measure what's going on is by adding in a tag, oh dear, that's not wrong. Is by adding in a tag to everything that synthesis makes. And so if I start chucking into this protein pool some red brick, and then just at random, synthesis will probably pick up a red brick and make a protein with it. And then I've got a trace of what's been going on. And now I can measure what synthesis is doing. And if any time I stop the experiment, which would be equivalent to taking a sample of the muscle, then I can take a measure of how much new protein has been made. So here we're using red bricks as the tracer, as the tag. But in actual fact, as I showed you, we can use heavy water, deuterium, to tag each new protein that's made. And, sorry. Okay, so if we stop there and thank synthesis. So that's what we end up with at any particular point in our experiment. And what's, I should be moving on the slides at that point as well. And but what the main advantage though of being able to add in proteomics to this, so this process of having a tag has been around for a long time. It's a very trusted technique of labeling things that are being made. But what we haven't been able to do until now is do this, which is get all of the blue ones together and say how many of this specific protein has been made. So now we're at the level that we can isolate the protein, identify what it is. We can take samples at different, we'll have samples at different times in the experiment, and so we can see whether this protein is becoming more abundant or less abundant, and we've got a measure of how hard synthesis was working. So when we've got those three things at a protein-specific level, just have to let my slides catch up. Oh dear. When we've got those three things at a protein-specific level, if you know two things, so we know the abundance and we know how hard synthesis was working, then you can work out the third. Now I admit there are some assumptions in this, but really this is the first time we've been able to get down to this level of detail. And this is the work that we've been doing. We just published it this year. And I'd just like to finish with the data, but probably a bit heavy for a Friday evening. But I wanted to illustrate the sort of things that the data can tell us. So often we would do this type of experiment with two groups. We'd have one group that's not exercising and would measure the normal rates of protein synthesis and turnover in that muscle, and a group that are exercising and we do the same, measure the protein synthesis. And then when we do that, we're able to plot the data on a figure like this, where we've got changes in synthesis between expressed relative to the control. So compared to the control group, the exercise people have more synthesis going on. Synthesis is working more. Or compared to the control group, the exercise people have less synthesis. And equally, left to right, we have an increase in abundance or decrease in abundance. But it's not necessarily the straight up and down that is so interesting. What's really interesting is when you look diagonally, and any dots that end up in this top right quadrant are an increase in abundance because synthesis has increased, or a decrease in abundance because synthesis has slowed down. But then even more so, if you look in the opposite diagonal, then you can get an insight to breakdown. If you remember, we've not had this before because everything that breakdown does goes in the bin. But now we can see that the abundance has actually decreased and that's because the rate of breakdown has increased more than the rate of synthesis. And oppositely, we can see abundance increasing because the rate of breakdown is even less than the decrease in the rate of synthesis. And as I say, this is the first ever time that we've been able to do this. It's the first data in the world that's shown this, and we've been able to do it in human exercise. I couldn't resist showing you some real data, so these are the real data. For the blue dots on the left are the sort of contractile, the sarcomeric proteins, and the orange dots are the enzymes that provide the energy for muscle contraction. Here's our friend myosin 2A. You can see that in response to resistance exercise, this protein is increased in abundance and it's synthesized more. So that's the work that I've been doing. That's kind of our latest and greatest work, if you like. And it brings me to my closing statements. And I was thinking about professorship, and I was thinking whether it's the start of the end or the end of the start. And by that I mean that for a long time I've used it as a goal or an endpoint. So I was quite surprised how quickly that changed. As soon as I got the letter that I was awarded professorship, all of a sudden it became a starting point, and it gave me a renewed energy to take on bigger questions like this. So I think really it feels like the end of the start to me. Don't want to upset the PhD students here, but I feel like I'm just coming out of studentship again, and I actually now have the tools to really do something important and interesting. So that's how I feel. And that's a great feeling to have. So I'd just like to thank the university, and in particular the Research Institute of Sport and Exercise Sciences, for being such a great environment for me to develop my career and for having so much trust in me. My directors, I spoke already about Tim. Tim was my PhD supervisor as well, alongside Dave. And Tim given me a lot of support. He's been a great manager during his time as head of the school as well. I'm not sure, I said this to him when a few years ago, I said, I'm not sure what Tim's management style is, but it fits me very well, so I felt very happy here. I received great mentorship as well from Tom Riley and from Keith George as well as head of Rises, and I'm still receiving great support from both Bill and Dave, even though I do tend to cost them quite a lot of money. I've got lots of collaborators. I've tried to list everybody here, so I've got many collaborators and work, and couldn't really have done this work without the support of the whole research team and staff within this university and across the world as well. I don't have time to thank everybody, but there is one person I can't see who's gone, Ben Edwards, that I'd like to thank in particular, because Ben has been a research collaborator and also is my right-hand man on the MSc Sport Exercise Physiology course. He's also a great friend, and he's really helped me immensely in teaching and being able to teach students and wider audiences. So if this lecture hasn't worked, then maybe some of this is wrong. My last slide, and it is my thanks to my wife. I'll say it quickly now before I start crying again. And you know what, when I wrote this slide, I found out that this traditionally feminist quote is now actually sexist, because you can't say that the woman is behind the man. You've got to say the woman is right next to the man, which she is. Well, anyway, I'm going astray now. What I wanted to say is that I hope I've got across it has been a long journey, and Sarah's been with me every step of the way. And it is a team effort. You know, it doesn't work without her. And so probably half of this professorship is owed to Sarah. And so I'd like to give my very special thanks to her. And close. Thank you very much.
Well, thank you very much, Jatin. I usually say at this point, thank you for a very informative lecture. And that usually means a little bit of science, but I actually didn't know about it. I can honestly say I've learned more about your background than I even suspect any other lecture I've ever been to for years. So it was really, really entertaining. There's a small memento.
Thank you very much.
You can't ask questions, as I remind people, because it's a professorial lecture. That's one of the privileges. But you can ask some questions outside. There's some wine and there's some nibbles. You have to be quick though, because we have to be out of the building by 7 o'clock. But there's a but. As Dave said, this isn't the Christmas party. The Christmas party is over in the Tom Riley building, and I'm told it's going to be going on until about 10 o'clock tonight. So if anybody wants to drift over there after the nibbles and have a chance to talk to Jatin, they're more than welcome. When you organise the event, if you're coming, can you grab one of the unopened bottles of wine and take that over with you? Get through them all in the course of the next half hour. So thanks again, Jatin.
Thank you
Brilliant
very much.
talk, and see you outside.